Um, Hopefully you can hear me fine.
Yeah.
Um, okay, so today I'll cover some topics, maybe a little historical perspective on some materials development, and then where things are I see going in the future, especially as we move to higher frequencies and really targeted toward the 5G frequency range. I'd like to acknowledge Steve Perini, especially for all the hard work and high frequency measurements that he made. A lot of the data I'll show toward the latter portion of this talk, those measurements were made by Steve, and then the financial support from the Center for Dielectric Studies. Industrial Consortium at Penn State. I know this is an international meeting, so let me first introduce Penn State University. Geographically, we are on the eastern part of the U.S. Here is the state of Pennsylvania, and our university is located right in the middle of the state. And you can see here we're quite a large university. There are over 100,000 students across the Commonwealth. There's 50,000 students at Penn State University's Central Campus, but we have many other Commonwealth campuses and a world campus. So we have over 100,000 students in our university, of which 10,000 are engineering students. I'd like to think that we're probably famous for engineering, but I think we're also very famous for the ice cream that we make and serve. This building here is where my laboratory is. It's the Millennium Science Complex. We have nanofabrication facilities, characterization facilities as well, and it's a state-of-the-art building that really focuses on material science. Okay, let's just talk about the evolution of cell phones. I think many of you are already aware of this, but as we move from 4G and the frequency bands shown here between 700 megahertz and about 2.7 gigahertz, we can see that for 5G, there will be many more opportunities for antenna development, higher density of these sorts of structures. And we could also see along with that, we have an expansion of this frequency range, 600 megahertz to 6 gigahertz. I think there's a lot of activity as we look between 3 and 6 gigahertz. That's a very interesting area for materials and devices. But also what's really interesting from the research point of view is the millimeter wave, where we're looking at much higher frequencies, somewhere in the 26 to 40 gigahertz. And of course, we are hearing also at the research stage going even beyond these to maybe even hundreds of gigahertz sort of range, terahertz. So what I'd like to talk about a little bit is some perspective that we gained over the last couple decades working with materials for 4G, 3G, that sort of thing, and some of the ideas we're moving forward with for the higher frequencies at 5G. So just looking here at maybe just a small list, we'll get into more materials work a little bit later of some of the materials that I see out there that are used. Here we can see we start off with some low permittivity polymers, somewhere in the 2.5 to 3.2 range. I'll get into some of these details on the properties, but essentially you can see here for 5G antennas, we can see this sort of array on some sort of board that's probably a very low permittivity composite material. And then for some of these maybe higher performance, maybe even higher power sort of applications, we can see here ceramics, glass, low temperature coal-fired ceramics, permittivities are a little bit higher. And you can see here some traces, some metallization on these white substrates, typically ceramic materials for high power, high rel sort of applications. And then finally, looking here at some of these really high power filtering applications, we see these sorts of materials shown here, much higher permittivity values, low loss. And you can see here these basically ceramic discs are put in series here for a filter application. So that just shows some of the ways that these materials are integrated into devices. If we think about the important material properties for 5G, really they can be categorized in three major parts. First of all, the relative permittivity, I alluded to that in the previous slide. So whenever you see an epsilon sub r, that's the relative permittivity, also known as the dielectric constant, and I'll refer to that as dk. In this presentation, they are the same. And in the past, there was a lot of focus on miniaturization with higher permittivity values. I'll show some examples of that. And we definitely see we're trending toward lower dielectric constant as frequency increases. Typically, the permittivity range of interest is somewhere between 1 and 100. And again, going to lower permittivities as we push frequency up, where a lot of the emphasis will basically move toward thinking about dielectric loss. Here, just like with relative permittivity and dielectric constant, I do use two terms to describe dielectric loss, either tan delta or Q. They're basically inversely related for dielectric materials. Dielectric loss contributes to the overall device loss, but as I'll show later on, it's not the only contribution. There's other contributions we must think about as well, in addition to dielectric loss. And we are seeing that low loss is becoming more and more important, especially for these sorts of applications. And I'll give some examples for some transmission lines. Loss range is shown here. These are unitless numbers, so somewhere between 10 to the minus 5 and 10 to the minus 2. Recall that I think of these inversely between tan delta and 1 over q. So basically then that tan delta translates to the q between 10 to the 5th and 10 to the 2nd in terms of values. The other important aspect, I won't cover this very much today, but it is very important in terms of the temperature dependence, especially of the permittivity, especially for like filter applications and that sort of thing. We know that we need low temperature coefficients. So for every, say, degree rise, we would see a very small change in the permittivity value. So these are the three that we really pay attention to when we're designing new materials, ceramics, polymers, and that sort of thing. Okay, so let's just do some comparisons and do some mapping of these different properties and discuss some of these sort of trade-offs. You can see here we're plotting the Q on the vertical axis, and again, Q and tan delta are related in this way, so you can look at either side of the vertical axes here to get the Q or loss. And we're looking at a variety of different materials, comparing the Q values and the relative permittivity of these materials. There's a list down here. I won't go into them in detail, but you can see generally there's different ranges of material properties for different applications. The resonators that I showed you for the high power filters tend to be really high Q, very low loss materials. And they're somewhere in the range of 30 to 50. That's a sort of a sweet spot for the geometries of these, and also the low loss because of the high power. Typically, we can see like barium zinc tannalates, barium zinc niobates. They're almost all oxides. And then the next thing we are looking at are block filters, which aren't used so much anymore. I'll give some examples. They're typically higher permittivity, a little bit lower Q, higher loss. And then an area where we explore for transmission lines. These are low temperature coal-fired ceramics. Polymers would also be grouped in this category where we have low permittivity, somewhere in the 2 to 5 range, maybe 2 to 10 range. And then the Q values are somewhere between 100 and 1,000, depending on the frequency. This is normalized to about 1 gigahertz because these properties are also frequency dependent. And then at very high permittivities, there are applications for like decoupling capacitors and other sort of miniaturized devices, typically lower frequency in the maybe hundreds of megahertz range. And there we're dealing with a lot of titanates, for example. So just gives you the trade-off. And what's also interesting about this plot is we see that there's a general trend, right? As we increase the permittivity, the loss goes up or Q goes down. And we can see this trend, and it's fundamentally related to the polarization mechanisms that give you these properties. So if you have a larger polarization that gives you the higher permittivity, it will naturally cause loss in these frequency ranges. So there are trade-offs between these properties. Just one other point here is these materials have been grouped to be within certain ranges of temperature coefficient. So that was the third variable I talked about. And these are very low, I guess, low dependence of permittivity on the temperature, which is very important. Okay, and then the other way we can do some comparisons is just look at this temperature coefficient. Here we're plotting it on the vertical axis. It's in ppm, so we're scaled from minus 1,000 ppm all the way up to 400 ppm. These are very small changes of permittivity as we increase the temperature, Kelvin or centigrade. It's pretty equivalent for this sort of plot. And then we're plotting that with, again, the dielectric constant or permittivity. And what we see here in general are some ranges of material. So we can categorize these in terms of the polymers shown down here. Fairly low permittivity, somewhere in the 3 range. They're covalent. They have different polarization mechanisms that respond in a way that we see a negative temperature coefficient of dielectric constant. And as we have more ionic character of the material, a lot of oxides, we can then see that that temperature coefficient fundamentally changes from negative to positive. And then as we increase permittivity to very high values, we end up in these sort of paraelectric materials. It's sort of the high temperature range for as they go from a paraelectric to a ferroelectric phase transition. And as we're coming down in temperature, we see this sort of rise in the permittivity, which yields this negative temperature coefficient. And we can see here that we get really extremely negative numbers for the temperature for some of these really high permittivity paraelectric types. What really gets interesting and fun from the materials standpoint is trying to hit this 0 ppm with materials. So here you can see a variety of them. Some of the more common ones that are used are the zirconia tin titanates, and some of the perovskites as well are very, very popular for filters and have been for quite a while. I'll show one example. We're looking at a ceramic co-fire where we actually mix pyrochlores to get a very nice permittivity range and also matching the temperature coefficient. So there's some work that we did to consider all the properties. Just an example, sort of old school, but just to give you an idea of a very old phone setup. Obviously, these are replaced by bulk acoustic wave sort of devices, but it's good to sort of use this as an example of why high permittivity was important. And this block filter, we were working on different materials, basically to increase the permittivity of this existing material from 90 to 430 while keeping the temperature coefficient also low, and also the loss also very low. And just by going from 90 to 430, we could then miniaturize this quite a bit. So there was a lot of research at one point just focusing on trying to increase the permittivity to decrease the size of this. Of course, it's been displaced by even smaller devices in terms of saws and BAWs. But just to give you an idea of how permittivity helps you scale the dimensions down. Another sort of concept we were playing with was a temperature idea where an antenna idea where we had a high permittivity to miniaturize, but also then had some fringes of low permittivity to really help the efficiency of the antenna. And we worked really hard at the center material. In this case, it was a bismuth zinc tantalate or niobate. And as we started looking at these materials, we can actually tailor different phases to, you can see here, this monoclinic phase had a 60 ppm per degree C, so positive, and this cubic form actually had a negative. And so as we started playing around with compositions between these, we were able to tailor that to get a very low temperature coefficient near 0, but also have a decent permittivity for miniaturization and low enough loss as well, and compatible with some of the processes we were looking at for this antenna. Just to give you an idea, this was a patch antenna with aluminum oxide. I think this was in the 600 megahertz range, and we were basically miniaturizing that with this high permittivity material. So just to give you an idea, oh sorry, it's 900 megahertz. Just to give you an idea of what can be done again with higher permittivities and miniaturization. Okay, so that really covers the dielectric material aspects. Let's look at more at the device level in terms of the conductors as well, because that's really important. So I've talked quite a bit about dielectric loss. of a material. But what you'll see in transmission lines is that the conductor loss is also very important. And we need to think of this holistically in terms of the contributions of both of these that will yield the final attenuation of your transmission line. So here's some properties that we look at. Again, dielectric loss range is somewhere below 1%. And here, resistivity ranges shown here are very low for some of these metals. So sort of standard transmission lines, looking at microstrips, coplanar waveguides where you have conductor on top on the same basically plane, the ground plane and the center conductor, and of course then waveguides. These are all transmission line structures. They've been studied extensively for their characteristics, impedance, and loss. If we just take one example where we were looking at low temperature coal-fired ceramics, in this case we were looking at the attenuation in terms of the attenuation dB per length. And here's the frequency, and it's pretty evident that as we push these higher frequencies that I mentioned for the millimeter wave, that this will get very high. Remember, dB is a log scale, so this is really increasing rapidly as we approach those frequencies that we were talking about for 5G. And the other thing that's really interesting with this plot is that we have a comparison of different dielectric materials. FR4 shown here, some Teflon base or fluoropolymer shown here, and then some ceramics. So you can see that there's a variety of attenuation lines depending on the dielectric, and also, which is not really captured here, is for a 50 ohm impedance, you actually have a different conductor geometry as well, which also kind of contributes to this. But basically, as we can see, we increase frequency, we definitely get an increase in this attenuation per unit length. So just kind of doing an accounting sort of exercise, and again, this was done a while back, where we look at the different contributions to this attenuation. So power in, power out, and the attenuation is really related to what fraction makes it out for the power, the microwave power, and we could actually total up the contributions in terms of a dielectric contribution, a conductor contribution, and a radiative contribution, and this has been done in terms of the conductor, basically broken out into two contributions, the metal and the surface losses, surface roughness, because we know there's a skin depth associated with this as well. As we push to higher frequencies, this will become more important as well. And so we can then do some accounting, add all these up to figure out their contributions to the total loss of the microstrip. As you can see here, radiation losses, at least in this frequency range, sub 10 gigahertz, I believe, was pretty low. But we can see here, at least for this dielectric and metal, we had pretty much equal partitioning of the contributions of the loss of the metal and the dielectric, so both contribute. At Penn State, we do a lot of work just because it's a little bit easier to look at maybe a resonant structure for quantifying these losses. It really removes a lot of calibration that we need to do. We look mostly at the resonant frequency, so it's a little bit easier for us to do this. And so I've been showing the attenuation per unit length, but it's fairly straightforward. If we just take that microstrip and form a resonant structure, in this case a ring, we can then basically relate that attenuation to something called a Q factor or loss. So I'll be talking about the ring resonator in the next few slides, basically because it's a much easier structure for us to do materials work on. So just going back, recall that when I talked about the attenuation or alpha for attenuation, the contributions of metal, radiation, and the radiation losses, and the dielectric. The same thing is shown here. We have, instead of alpha, we have Q, and we have the same contributions, the dielectric, the conductor, and the radiative losses. So what we can do then with that ring resonator, we certainly can measure the total Q of that resonator experimentally. And independently, we can also measure the dielectric fairly easily. I'll show that in the next slide. And we can then assume at this point that the radiation losses are negligible and the coupling losses are controlled as well. So what I'll show in the next slide is where we're actually getting at the dielectric Q. And if we know the dielectric Q and we know the total Q, we can get some idea of the conductor contribution to that overall device loss or that transmission line loss. So let's just get you warmed up on some measurements here. I'll talk more about that in the second half of the presentation. But this is a very nice way, a split cavity method. There's a variety of them, split post, split cavity. I'll get into that in the second half of the presentation. In this case, we measured an alumina substrate, permittivity around 9, the 10 delta, very low. If we look at the Q factor, very high. And so this is our substrate for our ring resonator, measured independently. And so we can use that to back out the conductor losses. So this is an experiment that we did where we screen printed on different conductors. In this case, I'll show a comparison between silver paste and nickel paste. You wonder why I would ever study nickel paste. We had some projects on multi-layer ceramic capacitors where the industry really moved toward nickel. And as they're pushing these decoupling capacitor frequencies higher, there's a lot of interest in nickel because it not only has a lower conductivity, but it also has a permeability that could contribute maybe to the performance of these devices. So that's why we studied nickel, and it also really was a good instructive set of experiments to show the differences between different metals that we could screen print on a ceramic substrate. So here you can see the nickel conductivity is about double. I'm sorry, the nickel conductivity is about half of the silver conductivity. And we made a variety of these rings and tested them. The way we did the measurements, basically after we screen printed on these rings, the bottom conductor ground plane is not shown here. We were able to then load that up into our fixture, converting the coax to microstrip, shown here. And of course, then we put this fixture, tied it up to our network analyzer, shown here. And the data we retrieve from that is shown here, just an example where we show the resonant frequencies here. So these are basically harmonic frequencies of some sort of integer number of wavelengths running around the circumference of this ring. These are some very early simulations that we did, some finite difference time domain, some homegrown code to actually just model the electric fields in this case. And you can see this basically representation of the different harmonics shown here, where we basically have one wavelength as we run around this ring. And you can see here at the second harmonic, you basically have two wavelengths running around this ring. So you can see the data. We're basically plotting that transmission coefficient versus frequency. We'll focus mostly on just the fundamental mode at this point. So looking a little more deeply at this fundamental mode, again, looking at the transmission coefficient, the amount of power making it through the ring resonator structure as a function of frequency, we can actually get this Q value by looking at where the resonant frequency is, FR, and then this peak width. And by this relationship with the peak width, so the wider the peak, the larger the delta F, the lower the Q. And we can get some measurement then of the Q of the device, right, by measuring that peak resonant frequency and the width. And that Q is basically related to the energy stored over the energy dissipated within any resonant device. Okay, so we now have a device measurement. We've measured our ring resonator. We have the same dielectric substrate, the aluminum oxide substrate with a very high Q value. And let's go ahead and look at the results for these two different metals. So you'll note here we actually did the first three harmonics, n equal 1, n equal 2, n equal 3. We compared the nickel ring and the silver ring, both on the same substrates. And here we can see the Q values. You can note then the total Q here for the ring resonator is substantially lower than the Q of the dielectric. Remember, the Q of the dielectric was 1400. So here we're at 30, 50, and 83 for the nickel. And for the silver, we're at 90, 152, and 160. And you can start seeing, remember that the nickel conductivity is half of that of silver. So basically, we can see here the Q value of the nickel ring resonator is half of that of the silver. So that's really interesting. The relationship is a little different at lower frequency. I'll get to that in a minute. But basically, you can see here we're about maybe 1/3 instead of the 1/2. And that was of interest to the folks making the multi-layer ceramic capacitors, because there's another thing that affects this surface resistance of a metal. And so if we think about the contributions, this is really contributes to the loss of the microstrip reflected in attenuation, or Q. And we can see here it's related to the frequency as well as the conductivity or resistivity. So we know this, remember that nickel has basically, in this case, it has double the resistivity of silver. And then the other term that that's very interesting is the magnetic properties. So the relative permeability here. That should be permeability, maybe not relative, but it's related to the magnetic properties. Okay, so because the rings are identical, it's very easy to sort of back out a very simple formula. If we know the Q factors for these different ring resonators, and we know the DC conductivity, the only really unknown was the permeability. And we can see here, at least for the measurements we made, the permeability for nickel, it's a magnetic material, fairly low. We would expect this at high frequencies, but it does contribute to the overall Q value of the ring resonator that we were measuring. So I guess hopefully the takeaway here is that in the experiments we did where the Q of the dielectric was so high that really the dominating factor was the metal. And we could actually explore metal properties by looking at these ring resonators. So that was pretty interesting. So let's just summarize here. In my research, I've looked at a variety of different applications. I know the ones for today, people are interested mostly in the ring resonators, microstrips, and also the dielectric resonators. But in my research, I've worked at Argonne National Lab where we're looking at accelerators, and there the problem is pretty much the same. Here we have a conductor, and we have an insulator, and the insulator is basically vacuum in this case, very, very low loss, and the superconducting walls are very, very low resistivity, super high conductivity. And so you can see here, at least for this construction, we have Q values of 1 billion, right? So incredibly high Q values because this structure is very, very low loss. I think the operating frequency is around 500 megahertz. And then, of course, we talked about the ring resonators quite a bit. Permittivity values are a 10 for the substrate, but more importantly, the Q value for the resonator is around 100 range, right? And then I also work on magnetic resonance imaging, and there we're looking at resonators for enhanced MRI signals. And that would be a separate sort of presentation. But what I find fascinating is the Q values we're competing with are 1. So here, because the body is so lossy, the Q value is actually -1 for the body, and our resonators are very, very low Q that we use to couple into the, in this case, you can see the brain scan. So I've played around with resonators basically over 10 orders of magnitude in Q, and they all have their different sweet spots for depending on the application. But let's go back to our 5G discussion here, where we're really focused on Q values in this range between 10 and 10 to the 5th. Okay, so just taking a step back then, just looking generally, and there's a lot of literature on quantification of losses in these sorts of structures. So you can see here that a microstrip, we can see the loss values are somewhere in the 0.05 to 0.5 dB per centimeter in general. Coplanar waveguides are fairly similar. I know there's a lot of variability here, and maybe the ranges can be extended a bit depending on materials and geometry, but this just gives us a discussion point anyway. And then what's really interesting, of course, as we go to waveguide geometries, the attenuation per unit length really drops, right? And it's a partitioning of the loss now. Basically, you have less metallization losses, right? More of the energy is basically, or power is focused in the dielectric itself. So as we push up frequencies, we need to think maybe about some new geometries for transmission lines. So let's take a look at that. Before this presentation, I looked back at some old notes, and there was a lot of work done on this sort of structure. And I've noticed that the literature and publication rate has increased quite a bit around these substrate integrated waveguides. Essentially what we're doing here, instead of a microstrip or coplanar, having like via fences and conductors top and bottom. And here, these are much lower loss transmission lines. We're always trading off sort of sort of process tractability or fabrication tractability with performance, right? So this is interesting. I'm starting to see more and more applications using this sort of geometry, mainly because it's fairly straightforward to punch vias and putting planar sort of conductors down. So this is a nice area to keep going with. It's been studied for a while, but I'm starting to see an uptick, at least in research interest in these sorts of transmission lines. And you can see the loss is quite a bit lower than what I showed on the previous slide for microstrips and coplanar waveguides, for example. All right, so let's just summarize this part of the presentation. Basically, the device design really, I think, dictates the material properties. You can get away with maybe a little higher loss material if the device basically already has conducting losses and you can tolerate that. So in terms of device design, it's really good to understand, where the material contributions come and what you can basically trade off. And here I'm talking about trade-offs. Knowing the fundamental polarization mechanism of material, we know that there's trade-offs between the dielectric constant, the loss, and the temperature coefficient. If you basically increase one, you'll probably increase the other two. And so these trade-offs need to be evaluated in terms of what you're trying to accomplish in your device as well. And then we know that the trends really, as we push toward these higher frequencies, we know we're going to have smooth metal traces. There's lots of great literature and tutorials here on using smoother substrates to get basically smoother conductors, and then your skin depths are smaller as well, and you're basically then lowering the loss of your transmission line by having a smoother conductor trace. Lower permittivity, definitely. We're not so worried about dimensional tolerances, or I guess we're always worried about dimensional tolerance, but just the actual dimensions. And we need to reduce dielectric loss at high frequency. So I think these are the trends that I see based on some of the devices we're focused on. All right, let's move into the next portion of the presentation, really looking at broadband dielectric materials characterization. If we look at sort of these many orders of magnitude of frequency here, going from very low frequency in the hertz all the way up to terahertz, so 12 orders of magnitude or something like that of frequency, and we can really get some idea of where typically the circuit world and the optics world sort of have their domains. Essentially, when we start thinking about measurements, we really need to sort of span those sort of concepts. And I'll be talking about specific measurement techniques in a minute. Of course, we work a lot with VNAs and also impedance analyzers at lower frequencies to do all the characterization. We have a suite of techniques to look at liquids, solids throughout this whole frequency range. More specifically, these show the techniques we have at Penn State and collaborators shown here. So here we're plotting frequency here, and we're going from basically 10 millihertz all the way up into the terahertz range. So again, looking at 13 orders of magnitude of frequency, and it's pretty valuable from the materials standpoint to look at this sort of frequency range, because generally dielectric relaxation mechanisms are very broad and they span many decades of frequencies. So to have this sort of capability is helpful when we're trying to understand loss contributions to materials and how to basically lower those loss contributions. So the first 9 orders of magnitude can be accomplished by a simple parallel plate method. We do adapt that a little bit to this terminated coaxial line, where we have a small sample basically on the end of a coaxial line, and then we have a large number of measurements that are available between 1 gigahertz and 100 gigahertz, for example. So I'll be focusing mainly on the high frequency for this 5G presentation. And one thing we try to do is take a common material. So as we're trying to understand sort of the relationship between these different measurement techniques, it's really useful to have a material that you can print into a variety of different geometries. So then you can put these these samples into the different measurements, we need like plates for free space. So that would be something that's on the order of 10 centimeters square, maybe 2 millimeters thick. But then for capacitors or split cavity, we probably need something a little thinner to get into the impedance ranges that we need. And then for split post or resonant post, we need, well, for resonant post, we need something that's a very tall cylinder, for example. And then for some of the coaxial line ones, we have very small samples. So I think 3D printable dielectrics just provides a way to have a common material that we can make into a variety of different geometries to then compare all these different measurement techniques. So the first one, just a low frequency parallel plate. It's pretty standard. You have metallization on both sides of a dielectric, and then you can back out from the capacitance measured by these impedance analyzers. You can back out the permittivity if you know the dimensions, and that's certainly very useful for many orders of magnitude of characterization. Just an example shown here for our 3D printable polymers. Here we're plotting the permittivity that is shown here. And here's the dielectric loss shown here in these red dots versus frequency going from 100 hertz to a megahertz. And we could already see something interesting is happening where we see this decrease in the permittivity and we see this change in the loss of the material. I'll talk a little bit about the polarization mechanisms in future slides, but you can learn a lot just in this frequency range and then build upon this knowledge when you start doing higher frequencies. So as we move up in frequency, a handy measurement to do is to basically just take the sample, put it at the end of a coaxial line. You have to calibrate a reference plane, and then from that we can then determine basically the impedance and then the permittivity. We do have ways of basically transitioning from the lumped impedance to a distributed impedance, because as you go to higher frequencies, the electric fields are not so uniform across the diameter of a sample, even though it's small. So we have ways of accounting for that as well. But the data is shown, I'll show the data a little bit later. And then split cavity. In this case, I did show that example with the aluminum oxide. Here we have something that's about 1 millimeter thick, a couple of millimeters in diameter, and we then put that sample right in the middle of this cavity here, and we can get these sorts of values at one frequency. So where I showed the parallel plate method, where we can go like 9 orders of magnitude or whatever in frequency, here we do a lot of work and we get one frequency measured here at about 17 gigahertz. We also collaborate with groups to do free space, shown here. And here we're pushing into the W band. So here we're looking between 90 and 110 gigahertz. And we supply these samples to our colleagues at AFRL to do these measurements on the same materials that we did measurements at lower frequency. So let's put it all together. So here we're looking at the relative permittivity versus frequency going from 100 hertz all the way up to 100 gigahertz shown here. And in general, we see this decrease in the relative permittivity as a function of frequency. So you can see here, split cavity, we had a Fabre-Perot technique. I didn't really cover that yet. And then we have transmission and free space. So those are all in here and they agree quite well. The other thing you'll notice is that we have this relaxation. If you ever see an increase in your permittivity as a function of frequency within this range, it's probably not correct. I don't think I've ever seen a material change in terms of increasing the relative permittivity with frequency. That's normally related to like inductance or some other error. So you always get some sort of decrease in the permittivity as a function of frequency within this range, right? If you go into the terahertz and above, that's a whole different story. In terms of the loss, so here we can see our low frequency, and then we actually have a little bit higher frequency adapter for that, and we can start seeing this peak, which will come down, and then we get yet another increase as we go to the higher frequencies. Of course, this sort of material that's 3D printable probably is not going to be used for a lot of 5G applications, but as I mentioned, it's very useful because we can make a variety of samples to basically compare and contrast all these different measurement techniques. If we look at just generically what's happening with materials as we span frequency, we can see here that we have the dielectric constant or relative permittivity, and we also have dielectric loss shown here. So we're going from very low frequency, 10 to the -2, all the way up to 10 to the 16th. Remember, our measurement range that I've been talking about goes up to about here and below. So really, a lot of what we're focused on then are these dipolar responses, especially of polymers. So I did show you a peak in the dipolar response for that material. And it's not as clean as what's shown here in the red line. Typically, because these polymers are semi-crystalline, they're not really that uniform in terms of their molecular makeup. Essentially, we don't get a sort of a very, very nice sharp peak, but we get some sort of distribution of relaxation modes. And a lot of times those tails will come up into the microwave and millimeter wave. The other thing is I'm going to show next is this ionic character. So in glass materials, we have a significant contribution because we have ions moving around within the material. And a lot of times those tails will come down into the 5G region. And so we have to really look at these mechanisms as well. So let's move on. As I mentioned in the title, I'm looking at ceramics, which I consider glass or ceramic, and polymers. So let's look at an example of a ceramic material in this way where we're looking at fundamental polarization response. So here's the broadband dielectric properties of pure silica glass. So in this case, the permittivity shown here, it's around 3.8, really doesn't change very much up until very high frequencies. And then here's the loss, or tan delta. And you can see here we're plotting a log scale. So as we sweep from the kilohertz range into the terahertz range, we're going up 4 orders of magnitude in the dielectric loss, where you can see here we're changing the relative permittivity actually very little. And so you can see this peak here. And this peak then is very interesting because normally with oxide materials, we don't really see peaks in this frequency range. We either see peaks well above it due to ionic polarization or well below it. So glass is a pretty interesting material. It's also very interesting for devices, right? So it's very common in low temperature coal-fired ceramics to have some sort of crystallizable ceramic from a glass phase to a crystalline phase, or there's like a little bit of a sintering aid of the glass that's put into these sorts of tapes that are made for packages. And so glass is a pretty important component for a lot of applications. It could be a potential substrate in itself as we move to new ideas in 5G. Of course, at home, you might have some sort of protection thing for your microwave oven, so glass is used there as well. So it's an important material to study. One thing we're looking at as well, we're working with a small company just to look at structural materials because there's more and more interest in what's happening inside as we push these 30 gigahertz signals inside an office environment. So knowing the material properties and modifying them accordingly is pretty interesting. So we do have some projects as well, just looking at materials within this environment here. So if we think about window glass, we think about the composition. It is mostly sand or silicate oxide, but we do put materials like soda or sodium oxide or calcium or magnesium, and we tend to add these in mainly because they lower the melting point of the glass and make it easy to fabricate. Ideally, for applications, some applications we want really low loss. We want to minimize these sorts of additives, but the practical reality is for making something lower cost, you need to add these sorts of elements to actually just make the glass. We tested these over a wide variety of frequencies here. This shows some of the geometries we used for the measurements. And this is a little bit small, sorry about that, but this shows a loss over here going from 1 gigahertz all the way up to 100 gigahertz. And you can see here it's fairly flat, somewhere between 0.01 and 0.1. So the loss is fairly high for window glass. And here's the permittivity value, a little cut off there, but it's about 6.8. As we look at all these different techniques, they align very well through this broad frequency range. So that's window glass. And what we found was as we add these alkalis, we believe that we're changing the response of the glass. Normally, we don't think about dipolar response of oxides, but in glass, we do. And some of these tails and responses will come up into the 5G frequency range. And some of the ionic tails as well will come down into that range. And some of these loss peaks will spread out a little bit and really increase the loss quite a bit. We have studied this in detail. Just a recent publication in Applied Physics Letters is shown here, where we compared then, it's the same composition. Silica, remember, is just sand. It's silicon and oxygen. And so if you look at quartz, it has a very, very nice uniform structure on the molecular scale. You have these, you can see here the silicon are these little gray dots here, and then the oxygen are the little red dots. And then as we move from crystalline quartz to something that is glass-like, so fused silica, no impurities, you can see these nice little hexagons get a little messy, right? So now all of a sudden we may have extra atoms in there, and that provides a lot of wiggle room, so to speak, for this structure. And then we start adding impurities, like I showed the window glass. And in this case, we can see where these structures break up even more for adding sodium, or maybe in this case calcium. And then the one thing that's important is we've fundamentally looked at what's called the polarizability, which is related to the relative permittivity or dielectric constant. And here we're going from a number 4.87 all the way up to 5.89. Not much of a change. And in fact, the permittivity values aren't that different. Here you're at about 4.5 for quartz, and here you're about 6. So maybe, 20–30% change in the permittivity because of this extra motion within the material. But what's profound is really this graph, where now we're looking at the loss, right? So let's do this comparison between those materials I just showed, where here's the quartz, right? This is the crystal material. Here we're looking at loss, again, a log scale. So we're at 10 to the minus 5 range in our measurements. As we start adding, or just let's not even add anything, let's just look at silicon oxide in terms of crystalline and amorphous. And what you can see then, the amorphous material, or fused silica, all of a sudden in our 5G range is going from the crystalline value of 10 to the minus 5 range, a little over, to 10 to the minus 2. So even though the permittivity didn't change very much, the loss changed 3 orders of magnitude. And then moving toward our window glass, we can see here that we have other effects that we're looking at here, and then we still see a little bit, I think, of this this silicon oxide result here for window glass, but it is definitely dominated by some of these additives as well. So that's some of the research we're doing, pretty exciting and hopefully relevant as we develop new materials for 5G. I just like to close just with almost like a philosophy here of the way we think at my group at Penn State, where we know electromagnetic simulation has advanced very, very much over the last couple decades, from some of our homegrown finite difference time domain codes to now things that are very user-friendly, widely available to students here, and it really has been a big change over the last couple decades in terms of simulation. We continue our materials work in a couple ways. One is understanding fundamentals. Also, just providing these sorts of properties in the ranges of interest for 5G, frequency ranges of interest, are really important as inputs to simulation. We're starting to see more and more of that. And I guess maybe this would be great for a discussion as well after the presentation is, I always get requests for very specific frequencies, when the reality is if I can measure below and above that frequency, I can give a pretty good idea of what that loss of permittivity will be. But I think the folks that are doing the simulations really want data exactly at the frequency they're doing the simulation with. And then, of course, as we start doing the design, then we start thinking about how to make things and what are tractable processes, how to make antennas, windows, all these sorts of things. So that's also very exciting. We're working with architects. We're working with a lot of other folks that are doing different designs of antennas, for example. So it's a pretty exciting time for 5G. With that, I think I'll conclude and then thank everyone for their attention.
Great, thank you very much, Mike. I would just remind the attendees that you can submit your questions through chat. So Mike, we have I think there's an echo, so I apologize. But the question is, are free space and focused beam the same technique?
Yeah, I guess I use those terms a little loosely. So free space, we have basically two techniques. We have the Fabric Pro Resonator, and then we also just have like horns that basically send the waves out, and basically we look at reflection and transmission coefficients to get the permittivity. So yeah, they are pretty much the same thing because I use those terms loosely, but there are a couple different techniques that I call free space. One's a resonant and one's a transmission technique.
Okay, I don't know if you can see on the chat, there's a few more questions coming in. Are there any approaches to increasing Q with implementing air voids?
Yeah, that's a really good way to do it, right? In terms of like vacuum has a very low loss. And so that accomplishes two things by adding porosity. One is it lowers your permittivity, and two, potentially it could lower your loss. I think the one challenge from what I've seen, at least in the materials that I've dealt with, is that as you have increased porosity, a lot of times those surfaces aren't super pure and maybe they'll pick up a little water, that sort of thing. So it is good to increase the porosity as long as you can control the surface and minimize any absorbed species, because that becomes really important for loss.
Thank you. And then another was, could you please speak more to the thin films you showed in the plot at the beginning of your talk?
So thin films have their own challenges to measuring the permittivity and loss. Because they're on a substrate, you have to figure out a way to remove the substrate contribution to actually get at the measurement of the properties for the film. And so there's a variety of ways to do that. One way is that we use the split cavity to back out the substrate permittivity, and then we deposit films to then look at the difference between the substrate permittivity and the film permittivity. So that's in terms of measurements, I believe, if they're asking about dielectric materials.
Thank you. The next one, is there a way to get more continuous data versus frequency in the higher 5G range? For quartz, there seems to be more data points.
Yes, that is one of my favorite questions. So one thing, you always have these trade-offs. Generally, there's two general types of measurements. One's a resonant technique, and then one's a reflection transmission technique. And if you want to measure really high Q samples, you really need to go for the resonant technique. And once you go for the resonant technique, you really then have fixed frequencies. And I've seen some really nice work in NIST, for example, where they've taken a cavity and look at a variety of modes. And so within that one cavity, like I showed just one data point for that split cavity, what they've done is they've taken the modes and they were not only getting one data point, but they were probably getting 20 data points through a frequency range. Still discrete, but it still gives you a resonant technique for high Q and somewhat of a broadband as well. That's always a trade-off. It always will be, because there's fundamental differences between a transmission reflection measurement and a resonant measurement in terms of bands, right? Yeah, that's a really good question.
Great. Okay, we have 3 more. I'm going to take two shorter questions first, and one is how would you explain the difference between the fused silica and quartz DF in the gigahertz range?
All right, so let's see if I can get back to my, so the quartz itself is crystalline, right? And so what happens is there's no real degree of freedom. Basically, the structure is really locked, and so there's no opportunity then, or less opportunity for the ions to move, and so then they don't create a loss. And then if you look here at the fused silica, because it's a more open structure, it has extra movement, and that's captured in this polarizability term here. And so that is just the way the materials are, and that's just what we're given from nature, is this this degree of freedom, this extra freedom with the glass structure.
Great, thank you. And then actually, speaking of NIST, Nate Orloff, you've submitted a question. You may want to give that in person because it's quite a long question here on the chat. So if you unmute yourself, perhaps you could, we'll take this as the last question today. Thanks, Nate.
Yeah, hey, Mike, that was really great. I really appreciate the talk. When I measured fused silica recently to a terahertz with the on-wafer techniques, I didn't see a appreciable loss up to 1.2 terahertz. And we just got the cows working up that high. So can you talk a little bit more about, like, I definitely didn't see anything with pretty good uncertainty to 325 gigahertz. So can you tell me, so like 1.1 to the 10 is 10 gigahertz, right? And 1 to the 11 is 110, right? And then, so like, is this plot claiming that you see loss at like 300 gigahertz?
So
Silica?
let's see. So on this, it'll be right in here. Yeah.
Yeah.
I didn't see that. Maybe there's like some uncertainty in these points. I wonder.
Yeah. So
I wonder about
couple
that.
things, couple comments. One is we did most of our measurements with the Fabre Pro resonator, which I don't really show here, but we can definitely talk about that. And then the other thing is I grabbed a lot of literature. Some of that's shown down here as well to get this plot. So yeah, so literature and measurement. I don't have the plot here, but I showed where our measurements align with literature to generate this sort of thing. I must admit the endpoint here is I'm not sure about it completely, so I don't know if it's going to keep going, but it sounds like it won't based on what you're telling me. For fused quartz, it's going to be coming down, maybe. I don't know.
Yeah, I didn't see this. I didn't see this upturn in my loss of the UHP fused silica that I measured, but it could be different fused silica too. I don't know.
You know, it's true. They're made differently. So some are made with like a fusion process. They might have some hydrogen in. So that's interesting. Maybe I need to go back and revisit that. That's interesting.
Yeah, I can show you the data that we have to 325. So that's like DC to 325. And then my next question is about the substrate integrated waveguide. So I'd expect that be mostly appropriate for analog waveforms, because digital waveforms might get clipped by the cutoff frequency of the waveguide. So like analog signals can propagate good through like a the beauty of a CPW is it can carry, or microstrip is that it can carry both digital and analog, but waveguide, is that right? Am I thinking about this right?
Oh, I'm sure there'll be a cutoff.
Yeah.
Right.
Okay.
So given the time, sorry, Nate.
Yeah, no, that's fine.
No, this is very interesting because I wanted to plug in a little bit about the iNEMI, put a plug in for the iNEMI project, since just now the fused silica discussion came up. So for everybody in the audience, we do have a very exciting iNEMI project with looking at basically characterization of and standard methods of characterization for high frequency materials, coming up with standards, and we'll have a lot of discussion also in measurements of fused silica, which we've just acquired as part of the reference. So if anybody is interested, and of course, Mike and Nate and a lot of others in the audience are part of that project. And so if you have any questions on that, please contact iNEMI. As well as the fact that we have a lot of interesting questions in the chat. I will be compiling the questions and sending it to Mike separately, and hopefully we can figure out a way to communicate it back to the audience. I'll figure out a way. Okay, so should we wrap up, Grace?
Yes, I think so, and thank you, Irma. Yeah, we've got lots of questions, and I believe we have email contacts for everyone, so we will be able to reach out individually when we map the question to your email, and hopefully get a response directly to you. But thank you all for your interest, and thanks, Mike, in particular. A very interesting talk today. Thank you.
My pleasure. Thank you.
Thank you, Mike.
Thanks, Irma.
So thank you all, and hopefully you can join us on the next 5G session, which will be in early May.
Yeah, it's exactly 4 weeks from now, and Nate Orloff from NIST would be our speaker for just 4 weeks from now. Thank you, everybody.
Bye-bye.
Bye.